All right, so let's talk about the greenhouse effect. All right, so here's the idea. Right, so we get all our energy from the sun. Okay. So here's the sun, here's the earth. And by the way, so we are getting electromagnetic radiation. We get 1400 watts per meter square. Okay. So a meter square is roughly the size of tabletop and like a study desk. And so if you were in space, every meter square is getting 1400 watts. And now, so that's the radiation coming from the Earth, from the sun. Okay, and if the Earth did not radiate that much heat out, then the Earth would warm. So you're getting so much energy, equal amount out. Okay. It turns out that if average it out, I mean it's daylight 12 hours a day. So the Earth, every square meter of the Earth is receiving 235 watts per meter square. Okay, every square of the surface of the Earth. And if you, on the average, if you're not radiating out 235 watts per meter square, then the Earth will warm up. So you need to have that equilibrium. So this is the incoming radiation. If this needs to be the outgoing radiation. And so back in the 1800s, this was true. At least that's what we believe. Okay? So the incoming amount of radiation was equal to the outgoing amount of radiation. If this somehow decreases, then the Earth will start warming up. How do we decrease this? How does we don't want to decrease this. We don't want to mess with this equilibrium. And we've been messing with this equilibrium for the last 50, 60 years. So here's what happened. So here's the Earth. And by the way, so what we are getting from the sun is visible light. And what we are emitting is infrared radiation. And that's so infrared radiation. Okay. What we are emitting is infrared. And what we are getting is mostly visible light. Okay, so here's what's happening. What we are doing is currently we are getting our energy from fossil fuels. And when you burn fossil fuels, okay, so it's essentially carbon and okay, it's a hydrocarbon. Okay. I'm not balancing this equation. When you're burning it, you're combining it with oxygen, and what you're producing is H2 and water. And this guy is the culprit. Okay. When you remember, we are emitting infrared radiation. Okay. Infrared radiation. And when you increase CO2 levels in the atmosphere, CO2 absorbs this infrared radiation and will emit it back equally in all directions. Okay, so essentially, all this infrared radiation is trapped. Okay, so CO2 is trapping the infrared radiation, and hence the infrared radiation, the 235 watts per meter square that we are supposed to emit has decreased. It's decreased by 3 watts per. In 2018, it was 232 watts per meter square. We still are getting 235 watts per meter square, and we are only radiating away 232 watts per meter square. So we are trapping a lot of heat. That's the greenhouse gas effect. Okay. So the gases that we are producing are trapping this infrared radiation. That's the greenhouse effect. So we'll look at the numbers. So we are getting energy from the sun in visible light, and we are emitting infrared radiation. So back in 1700, the amount of energy coming in was equal to the amount of energy going out. And if you somehow decrease the amount of energy going out, then the earth will warm up. Okay. All right, so the energy coming from the sun is mostly in the visible light, and the radiation we are emitting is infrared radiation. Okay. On the average, you're getting 235 watts per meter square from the earth, from the sun. And back in 1700s, we were emitting out 235 watts per meter square. Okay. Okay. In the last 50, 60 years, what we've done is we've increased the CO2 levels, the greenhouse gases tremendously in the atmosphere. And so now we are radiating less. Okay. So back in 1700, there were not as much greenhouse gases, and more gases were, more heat was, there was an energy balance. Okay, and that's called radiative imbalance. So here are the culprits, CO2 gas molecule. And this shows you a little, yeah, so there's CO2 absorbing the infrared radiation. Yeah. Okay. So there's CO2. By the way, Venus has a about 95% of its atmosphere is carbon dioxide, and the temperature of Venus is 750 degree Kelvin. So that's a runaway greenhouse effect. Venus would actually be below 0 degree Fahrenheit without the greenhouse effect. Okay, so that's how much the greenhouse gas effect has warmed Venus. Okay, so here's this dotted line is the energy coming from the sun. So the flux of radiation versus wavelength, that dotted line. Okay, water vapor and so on the surface of the earth, this solid line is what you see. So our atmosphere absorbed this, the ozone layer absorbed all this radiation. The water vapor absorbed all this. So the solid line is what we see on the surface of the earth. Okay. So this infrared is what we emit. Okay. So from the surface of the earth. So if we had no atmosphere, that dotted line is what we would emit. And the CO2 in the atmosphere is absorbing all this radiation. The water vapor is absorbing all this. Ozone is absorbing all this. So this greenhouse gas that we are emitting is absorbing all this. It's preventing all that radiation from escaping into space. Okay. And it's trapping that radiation. So that is the culprit. Okay. So, and the water vapor is a secondary effect. You put in more CO2, the earth gets warmer, more water vapor evaporates, and so that's a feedback effect. Okay, so if you remove CO2, there will be less water vapor in the atmosphere. Okay. So what this slide shows you is if we had no CO2 in the atmosphere, then the average temperature would be minus 18 degrees Celsius on Earth. And of course, we don't want that. So if we had 300 parts per million of carbon dioxide, then our temperature would be 14 degrees Celsius, which is good, which is what we want. And that's what we had in 1700. Okay. Earth has, so this is radiative forcing. When radiative forcing is, so radiative forcing is when we're not emitting This is the input of solar radiation, 235 watts per meter square. And if we are not emitting the same amount out, then we have a positive radiative forcing. Okay. And we have been in imbalance since 1970. So 1750 radiative forcing is taken to be zero then. That is, we were emitting as much energy as we were getting. Okay. Now here are the numbers. You can check, go to this Wikipedia site. These are 2018 numbers. The radiative forcing is 3 watts per meter square. That is, we are emitting 3 watts per meter square less in 2018 than we are getting. So energy is being trapped on Earth at the rate of 1600 trillion watts per second. This is 100 times greater than the rate at which we are using energy. So here's this puts in perspective. This is equivalent to exploding 20,000 atom bombs, like the ones that were dropped in Hiroshima, every second, and trapping that heat. That's how much heat we're trapping. Okay. And so, I mean, if that's warming the Earth, currently, well, so back in 1700, the Earth's temperature was 14 degrees Celsius. Currently, the Earth's temperature is about 15 degrees Celsius. Okay, 2020. You can look these numbers up roughly. And what our goal is, we definitely want to be below 16 degrees Celsius. Above 16 degrees Celsius, all of Greenland will melt. Okay. So, and so you guys can look those things up. So the current year-round average temperature is, well, about 15 degrees Celsius. This is a slightly older number. Okay. So here the temperature graph, so 14 degrees Celsius. This was okay, back in 1900, there was the temperature, and you can see that the average global temperature is rising. Okay. This is on a 500,000 year scale, so every 120,000 years we had these glacial periods. The last glacial period was about 15,000 years ago. Okay, so we are in an interglacial period now, and so this is showing you the temperature profile, okay, and so on. Okay, so 15,000 years ago, the temperature was about 9 degrees below what it is, 9 degrees Celsius below what it is now. All right. Sea levels have risen 120 meters since the last glacial period. So sea levels then were 120 meters below current sea levels. All that water was in glaciers. Okay. Now, if you melted if all the ice in Antarctica melted, sea levels would rise another 61 meters. Okay. If only Greenland melted, the sea level would rise about 7 meters. So Greenland would melt if this temperature rose above 16 degrees Celsius. And I suggest you guys go to that this link and see what the world would look like if all the ice melted. Okay. So these two fellows, this is a radio telescope. In the 60s, we're working with a radio telescope, and they pointed the telescope in every direction, and they were detecting a noise that they couldn't get rid of. And what they'd done was detected the microwave background radiation. So Arno Penzias and Robert Wilson. And it was the radiation left over from the Big Bang, which occurred 13.8 billion years ago. Okay. So an analysis of the distribution of the wavelengths of this radiation led to the deduction that the background temperature of the universe was 2.725 Kelvin. Okay. And what they measured was a uniform temperature. It turns out that we needed some variation in temperature, and so we sent out satellites to make more accurate measurements of this temperature. And you see, so those satellites measured up to microkelvin, okay, not up to, well, so they had they were measuring much more accurately, and they could detect 200 microkelvin variations. So these are warmer spots and these are colder spots. And it was important to detect these because a colder spot is where galaxies were formed and so on. Okay. So that's what the satellites did. All right, so that finishes this chapter. I had to go through this fairly quickly because we had quite a few slides. But so that will be our goal. We will finish one chapter a day. Okay. And so